Good morning. Here we are back in physics lab. Lab reports from last week are due, but this week in lab we're going to be looking at acceleration. So we've been studying kinematics, and we want to see what acceleration looks like in this laboratory setting. We're actually going to be, our objective for the day is to measure the gravitational acceleration g. So we've been looking at this in class in chapters 2 and chapter 3. So if we have something and we just drop it, at what rate will this object pick up speed? So I've got this metal disc. It's 100 grams, it says. If I drop it, how can I measure the acceleration? Now when I drop this, things happen pretty fast. So I can imagine getting a timer out and trying to time this, or maybe we could go over to the tower building and drop it from the 8th floor. Ooh, that would be a good idea, and we could time it there. That would be fun to do. But what we're going to do in class today in the lab room is we're going to take one of those 100-gram discs, the one that I just dropped, and what we're going to do is we're going to try and take a series of precision times as it drops. So we're going to try and follow it as it drops and actually graph. You can see on the board there's some graphs here. We want to measure the rate at which it picks up speed, and we want to see what its displacement looks like as a function of time. Now to do that, what I've got is, I took the metal disc, well, a different metal disc, but the same idea, and I put a paper streamer onto it. So this time when I drop it, what's going to happen is I'm going to have a motor set up at the edge of a table, and the motor's going to be spinning pretty fast. We'll take a look at all this in just a minute. So I got a motor that's going to be spinning pretty quickly, and when I drop the streamer, it's going to pick up speed and it's going to undergo an acceleration. And now I picked this metal disc because it's got a pretty good mass and it's pretty dense, and that means that air resistance could be a pretty small effect. And that's what we want to be able to do. If we want to get a measurement of the gravitational acceleration, we need to start with something where the air resistance effect is going to be pretty small. Now, one option was to pump all the air out of the room here, which that would have been a good option to follow up on actually. But instead what we're going to do is we're going to go with our metal disc and neglect air resistance. So, you know, that can show up in our error analysis in the limitations for today. We can say, well, we were ignoring air resistance when we did the calculations. So here are the measurements. Here's the metal disc. Here's the paper streamer. Now I'm going to have a rotating motor. The rotating motor has a little piece of metal attached to a little chain that actually will, every time it goes around once, it will hit the paper streamer. So as the paper streamer goes by, this rotating disc comes around and it very regularly hits the streamer. Now the streamer's moving past at a pretty good speed, and so what happens then is you end up with a streamer, if you take a close look here, it will have a series of marks on it from the rotating motor. So along with the rotating motor, we have some carbon paper. So we've got some carbon, and again, we'll take a look at this setup in just a second. So we've got carbon paper next to where the streamer is traveling. So every time the motor comes around and hits the carbon paper, it pushes the carbon paper into the paper streamer and it leaves a mark. So this is pretty high tech, right? So as long as the rotating motor is reliably turning at a fixed speed, what that says is these marks are actually separated evenly in terms of time intervals. And what we want to do is take a look over here real quick. So let's talk a little bit about these time intervals. This is going to be a really important part of the lab. If this is measured incorrectly, then it's going to throw all of the measurements off. So the way we do the time interval is we have a strobe light which we'll also look at in just a second. We have a strobe light set up, and so as the motor is turning around very rapidly, the strobe light can be adjusted until it matches the rotational speed of the motor. Once it matches the rotational speed, it's going to make it look like that rotating disc is standing still. So again, what we'll do then is we'll take the strobe light time, and I actually did this in advance, so I've been playing around with the strobe light and with the motor. And what I found with the strobe light is that it suggests that the motor is turning around 2,120 times per minute. So it's a pretty good speed here. You know, it's like 40 times a second, something like that this motor is spinning around. Now, I wasn't so sure about our strobe light. Let me just, I can grab this and show you guys what it looks like. So here is the strobe light, right here. And so I'm going to plug this in. I can turn it on. So we've got a strobe light. And as you guys know, strobe lights, or may know, maybe not, strobe lights are designed to give us a very rapid burst of light and then turn off. And so it gives us a series of very quick bursts. And so what you can do with a strobe light to calibrate it is I took a bunch of tuning forks. So these tuning forks that I'm working from, they're actually vibrating back and forth. And when I put them in the strobe light, they appear as if they're standing still. So I didn't use just one of these. I used a series of tuning forks. So I used a series of tuning forks, and I kind of went back and forth with the strobe light. And what I found out, not so surprising, is that our strobe light calibration actually is off quite a bit. In order to correct for the strobe light mismeasurement, we have to multiply by 1.14. We have a 14% correction to the strobe light. So there's a good example of a measuring device that is reading out a certain number, but it turns out by going back and double checking, it turns out that the number it's giving us is incorrect. And so I did. I went back. Now the tuning forks are pretty simple devices. So these, I'm hoping these are pretty reliable. So anyway, I took the strobe light reading of 2120 RPM, rotations or revolutions per minute, and I multiplied by this correction factor. So I kind of went back and forth and tried different frequencies, and it looked like in the region of the 2120 reading that the correction factor would be about 14%. So I multiplied by 1.14 and it says, aha, the strobe light was saying 2,120 RPMs, but in reality it's closer to 2417. So that seems pretty reliable. Now this is the strobe light reading that's corresponding to how fast the motor is turning. So, and again, there's a couple things going on with the motor turning too. We want to make sure that the motor is turning at a fixed, steady speed. And, I left the strobe light on it for a while, and you could see that it was pretty steady. There were a few times when it seemed like the motor either sped up or slowed down briefly, and then it kind of hit its rhythm again. Anyway, so the strobe light 2120 with the correction factor 2417. Now, what that says is the interval, this is what we're after, the interval between successive hits on the streamer, on the paper streamer, is found by taking 60 seconds, that's 1 minute, and dividing by 2,117. Now, I left some extra, when I multiplied by this, I left some other digits in there. Let's see. So it came out to be 0.02483 seconds, or about 25 milliseconds is the time interval between successive hits. So as you can see, it's a pretty short amount of time that we're looking at. So that's going to become the delta t for everything that we do. And we're going to find out when we come back and refer to that delta t quite frequently. So getting back to our paper streamer now, so what I did is I went through and I circled all of the hits. I took a look at the paper streamer, I put it on the table, and I identified all the hits. Now, early on in the paper streamer, there are so many hits by the motor when I'm just holding it. Here's what the scissors looks like. Here's what the paper streamer material looks like. So you can order this from our Physics R Us warehouse. And so I attached that on there. Now there's 3 runs that we want to do. So I've got a couple of runs already here, and I'm getting ready to do a 3rd run. And so what I've done is put this out on a table, identified where the points are, where the carbon paper marks are. And then from that, what we can do is start measuring distances. Now the early part of this, there are just so many hits, it's just not useful. So the early part, there's so many hits that have happened at that location. I can't tell where the true data is. And in fact, what was happening is this. So the reason there are a bunch of hits is because I'm getting everything in place. When I turn the motor starts hitting the paper. I haven't dropped it yet. And so all those hits end up in some place. And then at some point, when I feel like the motor speed seems like it's pretty steady, I just let go. And so I let go and the paper streamer is pulled through. Now you guys are thinking, but wait a minute, there's going to be not just air resistance, there's going to be a little bit of friction going on, and I think you're right. There are a number of items that could be slowing this whole process down. I'm guessing that it's more likely we'll get values of G that are below accepted values, probably more so than higher than accepted value. Although the timing is uncertain enough here, it could really go either way based on uncertainties in timing. So let's see then. So I took the first reliable data point and I circled that. So I got out my something to circle with. I got out a pen and I went through and I started circling these. I said, yeah, this is a good data point, and this one, and this one, and this one, and this one. And you'll see that. I can show you the runs that I've already completed. And then I measured. Now, the first point, I'm going to designate that as 0 centimeters. And then the first point out, so I've labeled these data points, 0, 1, 2, 3. Now, the tables are going to be much larger. There's going to be a data table for each run. And I think the first run I did, I got 10 good data points, and the next one I had 11. That's about the range of number of data points that we typically can come up with. So, 10, 11, 12 data points is probably what we're looking at for an individual run. And so what I got to do is I got to start from that 0 point and measure out each of those x values. Now I just made some stuff up here. The first point is 0. The next point, 2.7, I made that up. The next point, 5.8, and then 9.1. Now, the next column in my data table is to get the delta x. And if there's an acceleration going on, then I would expect the delta x's just keep getting bigger, right? As it goes faster and faster during each interval of time, it's going to travel a longer distance. And so that's what I am seeing, the delta x's, 2.7, 3.1, 3.3. Now, one thing I want you guys to recognize here and pay attention to is, notice that I started out with 4 points on the streamer. For each of those, I can write down how much time has, oh, I got that wrong. I need to change that right now. Let me get this corrected. Sorry about this. Actually, let me get this corrected, all right? Come back just a second. So what I needed to do there was get the times adjusted properly. So I've rewritten the numbers in the time column. And so the first time should be at 0. So x equals 0 and t equals 0, let's say. And so the first interval that goes by up to that first data point, that's going to be one of my delta t's. So I wrote down one delta t here. Now the amount of time that's gone by on the second data point will be 2 of those delta t's, and then 3, and then 4. So this entire column of times is going to be multiples of delta t. That's how much time has gone by. And you can see this is all happening pretty quickly. The entire drop to the floor takes just a couple tenths of a second. So we really do depend on the reliability of our delta t measurements. All right, so we've got that corrected. So here are the x's. Now notice, I think what we were starting to talk about is I had 4 data points here, but when I get to my delta x column, that reduces down to 3. I'm going to lose one of my data points because the delta x column is looking at differences between the data points. Now, from the delta x column, I can take each of the delta x's and divide through by delta t. So we talked about delta t being very crucial to our measurements here, our calculations, and we're going to divide through that by that number. What that's going to give us is a set of velocities. So velocity 1, velocity 2, velocity 3. Now the velocities are averaged between these pairs of data points. So the average velocity between these 2 times during that interval is that first velocity, and then the average velocity during this time, and the average velocity here. Now, once we've got all the velocities figured out, then we can do the delta velocity. So now, I'm going to be down to just 2 data points from my original 4. Now remember, you know, this original streamer, it's going to have like 10 or 11 or 12 data points. These data tables are going to actually be quite a bit longer. But notice that I've lost another row. I started with 4, and then when I did the delta x, I'm down to 3. When I do the delta v, I'm down to just 2. But from the delta v's, I can divide that through by delta t, and those will give me my accelerations. Now, what we've been talking about in class is that the gravitational field creates a uniform acceleration on all objects if there are no other forces acting on those objects. So again, neglecting air resistance, neglecting friction as the streamer goes through the motor setup, those kind of things, if we ignore them, then we should, or if they're negligible, if they're not an important part of this, you know, if they're not creating a slowdown, then we're hoping these accelerations will be similar to each other. So we're guessing that these are going to represent some kind of a consistent set of numbers. Now it turns out that doesn't really happen very often in this lab. And there's a reason for that. So a lot of times this is a lab where students are a little disappointed. You know, last week when we were doing, I think we were doing density measurements last lab, and I'm guessing those came out within 1% or so of accepted values, and they probably are reliable to that level. This turns out to be a bit of a rough lab. So we're going to get, and we can understand that why, because it turns out, looking at this data table, you might think, well, it looks fine. Everything is very systematically outlined. The problem we run into here is every time we do a delta x or a delta v measurement, the numbers that we end up with could be off by a millimeter or 2. Let's look at the delta x's. So what happens if this is off by a millimeter or so? Well, if this is off by just 1 millimeter, that's going to introduce a 5% error already. So that's going to be a 5% error. And then with the delta V's, we have the same kind of thing going on. So even though it seems pretty reliable, we're using all the formulas that we've developed in class, it does turn out that this is not numerically, there are kind of hidden problems with this approach. In any case, I feel like it's a useful lab because it gives us a chance to go through and really analyze. We're not just saying how much time does it take to drop to the floor. We're actually doing a series of checks all the way down. And so when we graph the data, so once we get the data table filled in, we get to graph the data. There's going to be a graph of displacement as a function of time. And what we've been talking about in class is, well, if there's a constant acceleration, that graph should look kind of like a parabola. And so we get to go in and check, does it really look like a parabola or not? And we'll see. We'll see if it actually does. Now, the second graph, now this is for each run, so there are 3 runs. They're going to have data tables with 10 or 11 data points across them. And then there are going to be 3 graphs here and 3 graphs here, so yeah, it's a bit much. But once you do one of these, then the others will follow along pretty quickly, I think. So what we always want to do on a graph is we always want to show the data very clearly. So make sure that the data is very prominent. You know, here I've labeled all my data points. Now, there's what's called a fit line or a fit curve. And that's some kind of usually a simple function that represents what the data is doing. With this lab, we actually expect that to be a parabola. So if you've got some practice with this already, if you're already familiar with going into, say, Excel or some other software, where you can create a function that represents your data, that's great. Go ahead and for the x versus t graphs, try fitting a second order polynomial. Try fitting a parabola. If not, you can just do it by hand. All right. For the v versus t graph, this should actually be, well, theoretically, we're predicting it would be a straight line. So what we're saying is that if the acceleration is constant, and you know, over this much distance of Earth's gravitational field, the acceleration effect should be pretty much uniform. What we would see then is that the v would steadily increase. That would give us a straight line. So again, if you're doing this in Google Sheets or Excel, something like that, then think of this in terms of fitting it with a line. And the slope of that line actually would be the gravitational acceleration, which is what we're trying to measure for the day in today's lab. So now we talked about this too, you know, it's important to get these graphs labeled. We talked about lab report formats last week in the first lab. And so if you've got any questions about lab reports or whatever, go back and take a look at the first lab, the last portion of that, where we talked about lab report formats. Now the time involved for the entire drop, like we were saying, it's just a few tenths of a second. So when I label my horizontal axis of time, that's probably going to be labeled as something like 0.1, 0.2, 0.3 seconds. So that's this axis. Now the vertical axes, the longest distance that we would collect data on these streamers is about 80 centimeters. So it's about this much distance. And that's because it's the height of our tables. So if you look at the lab tables here, what we're going to be doing is dropping the streamers alongside one of the tables. And by the time it hits the floor, I don't want to collect any more data. And by the time it's hit the floor, it's only traveled about 80 centimeters. So that's one of the things we're gonna watch for with our data. In any case, I've got graphs for x versus t, graphs for v versus t. I got the data table set up. We have the strobe light calculations with the ever so important delta t set up. We're going to be using this throughout. every time we divide by delta t in this, to get the numbers in this column, and the delta t to get the numbers in this column, we're going to be using that number. Remember, what that's keeping track of is the time intervals between successive data points on the streamers. Okay, so it should be good, right? We'll get a chance to see some x versus t and v versus t graphs. That's what we've been talking about in class. Let's do this. Let's go ahead and take a look at the setup. And I think to do that, I'm just going to grab the camera here, I think, and take a look at it. So, walking over to the table here, here is the setup. So this right here, this is the motor that we were talking about. Now what I've got is, it's an electric motor. You can see that there's some carbon paper right there. There are some staples right here. I'll get the streamer out and thread it through and show you what it looks like. But when we look up on top of the table, what we've got then is I got a battery set up with, I've got a switch here. And so if you look at all the wires, if I turn on the switch, here we go. There we go. So the switch is turned on, and if I come down and look at the motor, what I can see is that the motor is spinning around. In fact, it's spinning so fast, it's kind of hard to tell what's going on, right? But that's what we're going to be dropping the streamer through, is that right there. Again, here's the battery, here is the switch. I'm going to turn this off for just a second. Here are the runs that I've already done. And so here is one of my streamers. Let me see if I can get in and... Now there's data points. You can see that I've circled them. Let me head back here a bit. So I'm going to go back here a bit, and you can kind of see the lengths of the two runs that I've already done. There's the carbon paper over there, and there's the meter stick that I've been using. Ooh, and here is the lens, so I can get really close and get accurate readings with this. But that's what they look like. So here are the data points as the streamer was dropped. These are the hits that occurred when the motor came around. And so I've gone in and I've written down all those numbers. So I've got all of those copied down. I can show you those too in just a second here. So anyway, let me take a stop here and then show you a streamer following through. So here is the setup. I've taken the metal disc, I've attached a streamer to it. I've borrowed a brick to hold that in place for right now. If you notice, it's been threaded through a couple of staples. And so now what I'm ready to do is I can turn on the motor, and then I can position the streamer, and whenever I'm ready, I can drop it, and we'll see if we get some good data points. So here we go. See if this works. All right, that seems pretty reliable. I'm going to grab the streamer now, and here we go. 1, 2, 3. All right, so that's the procedure that we've talked about, and I'm going to take a look at the data and see what I've got. All right, so here is that third streamer, and I went back and I repositioned the motor so it was better centered, and I got out some new carbon paper too. And look, this is definitely the best set of data. I've got, let's count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we've got some early data, maybe too much. I might want to... But look, even very early, you can see where I was holding it when I turned on the motor. But that early data looks, entirely usable, maybe. I'll have to see. I'll get out and do the series of measurements. Just to see what the data looks like. Here's the data sheet that I have for run number 1, that first streamer over here. There's the data sheet, so you can see the timing and the distances. There's the strobe light measurement. Here is run number 2.
So I'll be writing that up and then providing the data sheets for those. So anyway, that's it's looking like we've got a good amount of data. So the issues that we may run into still, we have to consider, are uncertainties that we have because of timing, and then kind of the inherent numerical difficulties that I mentioned with the procedure. It's not, all of these data points aren't as independent as you might think. Anyway, if you guys have any questions on this, let me know. Stop by office hours.